Hi and welcome to MSc. In this video we're going to be looking at deriving the formulae for the three gas laws. The three gas laws in question here are Boyle's law, Charles's law, and Gay-Lussac's law. So let's start with Boyle's law. So in Boyle's law we hold constant N, which is the number of moles, and the temperature of the gas in question. That leaves two variables free to change in this scenario. And the variables that can change here are pressure and volume. So for this, I suggest you picture a balloon or small vessel of gas like a piston, and imagine what would happen if you didn't add or subtract gas, so N stays constant, and you're keeping the temperature the same, so the particles aren't going to change their speed and motion inside the vessel. If you pushed on the vessel, then the volume would get smaller. You'd squeeze it. And if you release the pressure, then the volume would increase. And so we can write this out as saying as pressure increases, that means the volume would decrease, and vice versa. Mathematically, what we can say then is we can say, well, the pressure is inversely proportional to the volume, and vice versa. Right? And so what that means is as one gets big, the other gets small, basically. And what's cool about proportionality is, generally speaking, if two things are proportional, we can make them equal by use of a constant. So we can say, well, the pressure is equal to a constant divided by the volume, instead of it being proportional to 1 over v, which means inversely proportional. One goes up, one goes down. Well, using this idea of a constant, I can rearrange this. And I can now say, well, pressure times volume is equal to a constant. And that simply comes from opposite of dividing by volume is multiplying on the other side. But what this really means is the product of any pressure-volume combination for that gas will be equal to a constant. So if I have an initial pressure and volume condition, that is equal to a constant, which is also equal to any later pressure or volume combination. So if I change the pressure, the volume will respond in a predictable way. By writing it like this, I really don't need that constant there in the middle. So the way we can write this is saying that the initial pressure times the initial volume is equal to the final pressure and the final volume. And this can be rearranged for any of these four variables. And this is Boyle's law, commonly stated as P1 times V1 equals P2 times V2. Moving on to Charles's law, we see that again what's held constant is the number of moles. In other words, we're not adding or subtracting gas out of our vessel, and the pressure is held constant. What changes here, the variables that will change for the gas, are the temperature and the volume. So for this one, we could consider perhaps a bottle, a water bottle, plastic bottle that maybe has been left in a car, and the temperature changes, and it'll change the volume slightly as a result. So if we're keeping the pressure the same, that means that if I have a higher temperature, the particles will be moving faster and would be hitting the walls of the vessel with more frequency and more force. So in order to maintain the same pressure, I would need to balloon outward, and the volume would grow. Conversely, if I had a lower temperature, particles would be moving less quickly, hitting the walls with less force and less frequency, and therefore I would need a smaller volume in order to maintain that pressure. So again, the way to write this out would be to say, as temperature increases, the volume will also increase. So unlike the first scenario in Boyle's law where they're inversely proportional, these are directly proportional to each other. As one goes up, the other goes up as well, and as one drops, the other also drops. So just like before, we can make this equal by use of a constant. So I can say T is equal to, and I'll just use C for the constant, C times V. Now this is a different constant, and if you've done a little bit of work with the ideal gas law, you have a sense of what might be part of that constant. But I'm going to use a prime notation to indicate that this is a different constant than what we had before. Okay? But similarly, let's put our two variables on the same side of the equation. So now I can say, well, T divided by V is equal to this constant, right? But also like before, this is going to be true for any temperature volume pair at that specific number of moles and pressure. So this could be my initial conditions, but it will also be equal to final conditions. And just like before as well, I don't need that constant in the middle of my formula. So I can simply say that T1 over V1 is equal to T2 over V2. And this is Charles' law. Now, unlike Boyle's law, there is an alternate version of this. And I'll say or. And let's think about this other version now. So if I have two fractions that are equivalent to each other, their reciprocals also have to be equivalent as well. So what that means is an alternate version of Charles' law is V1 over T1, which is equal to V2 over T2. And that is an alternate version of Charles' law. Now you might say, why does it matter that there's two versions? Well, it really doesn't. I suppose you can use either one in any Charles' law scenario. But when this one is helpful is when you're solving for temperature. If you're solving for one of the two temperatures, either your initial or secondary final temperature, then this one's useful because the temperature is already in the numerator. And typically solving for things in the denominator is a little more challenging. This other version of the formula has volume in the numerator. So if you're solving for volume, that makes this one step easier to rearrange and solve for the unknown. Moving on to Gay-Lussac's law, we again see that the moles is held constant. So in all of these scenarios, we are not adding or subtracting gas from our vessel. Here we're keeping volume constant. So it's useful, I think, to picture some type of rigid compressed gas cylinder, something that's made of metal that is going to resist any type of volume change. And what we can think about this is if I increase the temperature of the gas inside that vessel, well, then they're moving faster and they're hitting the walls with more frequency and more force, and that will result in a larger pressure. And then, of course, if I cool the gas, the opposite will happen. Less force, less frequency, less pressure. So what we can say is as temperature increases, pressure also increases. And you'll notice that that's a similar scenario to what we had in Charles' law. So I'd expect that our rationale through the derivation here will be very similar. So we can say that these are directly proportional. As one goes up, so too does the other. So we can say they're directly proportional. From there, we can say, well, I can actually make that proportionality equal with the use of a constant. Now this constant will be different than the other two. I'll use a double prime notation to indicate that. And I'll say that that's true when I multiply by the pressure. And of course, I would like to isolate my variables. Opposite of multiplying is dividing. So I'll say temperature divided by pressure is equal to this constant, which I'm calling C double prime. Now, this has to be true for fixed moles and volume for any temperature pressure combination that I can create for that gas. So my initial conditions and final conditions, and allowing me then to solve for an unknown value. Of course, just like before, I don't really want the constant in there, and this will generate Gay-Lussac's law, which is T1 over P1 equaling T2 over P2. And the similarities continue, because there's also a secondary version of this. Of course, this is useful if you're solving for temperature, and the reciprocal relationship will be slightly more useful if you're solving for an unknown pressure. And that is a secondary version of the Gay-Lussac law. So there you have a quick run through of a derivation of the three gas laws. I hope this video has been helpful. If it has, please consider liking this video and subscribing to the station. And as always, thank you very much for listening and watching.